started. And as I'm seeing, we're already recording. That's great. Awesome. So, welcome everyone to our March iteration of Glow. Thanks everyone for joining. We're going to have two great talks today. Um, Before we get started, I just want to very quickly introduce Franca to you. She's the newest member of our organizing team. And yeah, let's thank Franca, everybody, for joining and helping making Glow happen. Um, okay, so now that we have that, let's get ready with the talks. We're going to start with Steve. He's going to talk about 15 minutes. Then afterwards, Diana is going to talk also for 15 minutes. And afterwards, we're going to have breakout rooms, as always, where people can join their respective paper rooms and discuss with the authors. Yeah, so this is the usual Glow style meeting. Right. And so without further ado, I'd like to uh, give the stage to Steve, and we'll hear about GNN expressiveness. Explanations. I'm so
Explainability.
sorry. I'm so
No
sorry.
worries, no worries. No worries. Thank you, Luis. Let me share the screen. I hope you can all see now.
Yes.
All right. So thank you, everybody. Thanks also to the organizers for having me here today. My name is Steve, and I'm a third-year PhD student at the University of Trento. And today, I would like to introduce you to some insights that, together with my amazing collaborators, recently published at ICLR 2026. The structure of my presentation follows quite faithfully the title. So I would like to first introduce you to a family of explanations that do not really explain. This will be clear in a second what that means. And then we will move to how to find them. Before going to the actual meet, we of course need to set some background. And since this is the graph learning reading group, I assume some prior knowledge on graph learning, why graphs are cool, and why it's cool to study GNNs. And I will move straight to the explainability part. And I think that I won't find you surprised if I tell you that GNNs are black boxes. So once you train your model and you feed a test graph to your model that outputs a certain prediction, it is in general not possible to understand why it made a certain prediction and which features are mostly important for such a prediction. And I think that I won't surprise you either if I tell you that people have been proposing techniques to overcome these limitations, such as post-hoc explainers that work in a post-hoc manner by taking a trained GNN and producing an explanation post-hoc. Clearly, this comes with limitations, and it has been shown that post-hoc explainers can be unreliable, meaning that we are basically shifting the question from can you trust your model to can you actually trust your explanation, which is not necessarily a simpler question to answer. What's the solution then to go beyond this loophole? Well, one idea could be to design better models, where better in this case means more interpretable, or designing models with interpretability in mind. And a notable approach in this sense for what concerns graphs are self-explainable graph neural networks, SCGNNs in short. SCGNNs are composed as follows. They pair an explanation extractor, which is implemented as a standard GNN, which first outputs a subgraph, which now acts as an explanation. And this is achieved by either predicting edge-wise relevant scores or node-wise relevant scores, which are then, for example, thresholded or top K activated. Then this explanation is fed to a classifier, which is again implemented by another GNN, and the two models are trained end-to-end jointly. This framework became quite popular with several extensions and with different applications, for example, also to out-of-distribution generalization. Nonetheless, we should still be mindful about the following question. How good are these explanations at the end of the day? And the recent work have highlighted that even asynchronous explanations can be redundant, can be in some cases ambiguous, and they can be affected by spurious correlations. However, it remains unclear whether there are some pathological failure cases that we as practitioners should be aware of. And it is my intention in this talk to convince you that yes, in fact, there are. This brings us to our contribution. We first show that many popular SCGNNs can obtain optimal loss by providing what we call degenerate explanations, where by degenerate explanations, we mean a family of explanations that do not tell anything about the underlying model. Perhaps more spicy is the question of whether we can then actually detect degenerate explanations. So provided that these models have these failure cases, can we at least recognize when this failure case is happening? And as we will see, it is not that easy to answer this question. However, let's start from the beginning. Let me introduce you to this family of degenerate explanations. I thought that the best idea to explain what we mean by degenerate is through an example. So let me guide you through this example. Let us pick a set of graphs where we have a random number of nodes with random connectivity. And the task defined on this graph is the one reported on the left. So our graph has label 1 whenever the number of blue nodes is greater than the number of red nodes. Then we make sure that every graph also contains one single green node and one single violet node, which are always isolated from the rest, so that it is safe to conclude that these two additional nodes are uncorrelated with respect to the label. Now, I hope we can agree that an accurate GNNs must use red and blue nodes to make accurate predictions. And the perhaps surprising insight is that accurate SCGNNs can actually provide only green and violet nodes as explanations, which is in a sense counterintuitive. And this is exactly what we call degenerate explanation, something that in principle should not happen for an accurate model. We now move to showing that this problem can actually happen in popular SCGNNs. And I'm going to introduce you to the main theorem of our paper in a slightly simplified version for the sake of the presentation. Let me start by defining D to be a data distribution with a deterministic ground truth labeling function phi that maps graphs to their respective labels. Now, let me define calligraphic Z to be a set of single node subgraphs that are equally appearing in all graphs. To make this clear, I provide here an example in terms of the previous example. So a valid construction for this calligraphic Z is, for example, picking the red and the violet nodes as the individual sets. Then it is possible to show that there exists an explanation extractor E, which predicts as an explanation the subgraph indexed by the ground truth label, and a classifier which manages to retrieve the index of that specific subgraph, providing as an output the correct ground truth label. Such that the overall SCGNN obtained by composing E with G and as implemented by these 5 popular SCGNNs, which I'm not going to describe in detail now, achieves optimal true risk. This might not seem super intuitive, but let me provide an example that hopefully clarifies your mind. It is actually possible to construct the following explanation extractor E that outputs the node green whenever the ground truth label of the graph is 0, and output the violet node whenever the ground truth label of the graph is 1. And at this point, the classifier can simply learn to map the green node to label 0 and the violet node to label 1. And this means that the explanation is doing nothing but just carrying the label. It's just encoding the label that the explanation extractor inferred. A quite interesting remark, hopefully, is for people studying expressivity of graph models, is that the more expressive the explanation extractor is, the more labeling function phi can actually be learned and can actually be solved by degenerate explanations, highlighting a trade-off between the expressivity of the GNN that is used to implement the model, the explanation extractor, and how likely it is to end up with degenerate explanations. I'm providing here a couple of examples just to convey some intuition, but of course in the paper you can find many more. And in this case, I'm providing a couple of examples for the MNIST superpixel data set, where despite the SCGNNs achieving competitive performance, the explanation that are providing are just highlighting background pixels, which are not really related to the task being solved. Similarly, for a sentiment analysis task, we managed to show that accurate models just predict uncorrelated stop words as explanations. I think we can now move to the second question. Okay, I hope I convince you that there is this problem of degenerate explanations and can actually happen. And that is actually the optima of what these SCGNNs are optimizing for. Now the question is, can we actually detect when an SCGNN is producing degenerate explanations? And the way we aim to answer this question is through faithfulness metrics. Faithfulness metrics are a popular way to measure the faithfulness of an explanation. And all you need to know is that they can be divided into two main families, two different types. Metrics estimating the necessity and metrics estimating the sufficiency. Metrics for necessity perturb the explanation, aiming to observe some large shift in the predicted output probability distribution. Whereas sufficiency metrics, on the other hand, aim to perturb what's around the explanation. So you keep the explanation fixed and you start perturbing the complement, aiming to observe little to no change in the output distribution. And then the differences between all these different implementations are encoded in some assumptions that they make regarding the perturbation. So which perturbation to apply. For example, some of them remove the explanation altogether, or some other apply edge perturbations, or some other, again, apply some feature level perturbation. So now the question can be rewritten as follows. Given a degenerate SCGNN, how many explanations are actually marked as unfaithful by each metric? So if we count the number of explanations of degenerate explanations, how many of them are actually rejected or marked as unfaithful or as bad by these metrics? So what we did was to train a bunch of SCGNNs, making sure that they all extract degenerate explanations, and we computed all the previous metrics that I presented you. And the results are perhaps quite surprisingly, in the sense that basically all the previous metrics have some issues. So they may work well in, say, 2 datasets over 2, but in the others, they severely fail. And this is a big issue, right? Because this means that you cannot really trust the evaluation metric that you are using. To amend this issue, we proposed a fairly simple extension of the previous faithfulness metrics that, as you can see in the last column, manages to score the highest or second to best basically across all settings, meaning that this metric is much more robust across different scenarios and across different settings, candidating this metric to be a better way to audit explanations. And the main difference, if you let me go back one slide, the main difference between our metric and the previous one is that we are making no assumption about the distribution over perturbation. So basically, the problem of previous metric is that each one is picking a specific distribution over perturbation. And this immediately makes the metric invariant to all the other possible perturbations. In this way, by not relying on a specific set of perturbation, we managed to show and to achieve much more robust results, and also to prove some theoretical guarantees in terms of which are the explanations that are marked as unfaithful. And like this theoretical analysis was not reported in the slide for the sake of time, but you can find it in the paper if you're interested. This pretty much concludes my presentation. I just wanted to exploit one last minute to point out to some interesting future work. Of course, the SCGNN framework that I presented to you today is not the only way in which you can achieve interpretable by design graph neural networks. There are many others, like based on kernels, prototypes, additive models, or on logic. And we believe that degenerate explanation can actually be a nice theoretical and empirical benchmark for testing how explainable these models are. And in case they turn out that they are also affected by this degenerate problem, a nice question then becomes that of proposing new models that are provably robust to this degenerate explanation issue. With that, my presentation is over. Thank you very much.
Thank you so much, Steve. I appreciate you included at least a little bit of expressivity into your talk, to not make me look that silly. But anyway, thanks so much. Super interesting. Yeah.